Okay, this is TempleOS 5-minute random code walkthrough episode 87, and I'm your host, Terry Davis. And today, oh no, we are in the header file for everything. Okay, so the file we're in is in the kernel directory. It's called Atom1A. Atom1A has the class and define. There's no actual code in Atom1A. Atom1B and C have externs for functions. Atom1A doesn't have externs for functions. It just has class and pound defines. So I could do a quick run through from the top. It's a lot of code. It's 3,000 lines. So we have some forward definitions for classes. We have integer range defines. I like defines, not enum, because in fact I didn't put enum in my compiler. I just like it because it's simple, and if you can do it in a simple way, why do you want to make it more complicated? That's just one less. Well, anyway, so I have typecasting postfix, not prefix. So this is how you you can enter a 64-bit floating point double constant. You can make it into a float. So you should get familiar with 1.0 is 3 FF0 and then zeros. I like to say if I did a employment test, I might ask somebody to represent a floating point number. Anyway, so what else we have here? So there's my integers have what I call sub-integer access. What I do is this is kind of like bit fields. I don't have bit fields in my compiler, but what I have is you can tell it a if you don't have a if you make an integer like an I64I, then you can access it as I equals 1, 2, 3, but because it has a I64 is made up of sub-integers, let's say this was 0, 0x0, then you can say I dot U8 sub 1, and that's 1, that's 0x01. Anyway, so there's what I call sub-integers. So the compiler is a little bit different because you tell it what the whole variable is, and then you tell it what the parts of the variable are. So I is intrinsic. So an I8 intrinsic is I just bailed out. I didn't want to save my modified. Anyway, so an I8 intrinsic is then that's the actual internal type. So it's actually not any faster doing this. It should use bit shift, but this actually what it does, if you call a variable, if you access a sub integer, then it no longer uses register variables. So it's actually slower in most cases, which is kind of ironic. Oh well. So I've got complex numbers. I have some various data types, standard, two-dimensional integers. Well, anyway, it's pretty self-explanatory. So I have some intrinsic data types, my ordinary differential equation solver. This is kind of everything that's in the operating system shows up in this header file. Integer software interrupts and stuff, fault interrupts, the flags, that's the system flags. E flags. There's, I think, even though it's 64-bit, you only have 32 bits of system flags. The global descriptor table, that's for setting up protected long mode. Anyway, so this is the format for my binary files. My compiler makes its own binary file type. I have posted on my website a bin rep. If you go into the Terry files on my website, it'll help you see how the binary files are structured. They have a header, and anyway, bin file header, and then they have a table full of externs and imports and exports and stuff. So run levels, it's not very much like Linux. I set a flag when as it completes different stages during boot. Anyway, the local APIC. I don't really remember this stuff very well. Once you do it once, you forget about it after years if you don't touch it. So these are model specific registers. If you want to set the FS segment or GS segment, you actually have to do it with the model specific. EFIR is for changing to, I forget, 64-bit or long, I think it's for 64-bit mode. So, so at one point I had my global variables in separate, but then I bunched them into structures. So now there's a single structure for each group of global variables. When you do a sometimes you do some BIOS. There's the 32-bit BIOS, which is this is for the CPU ID instruction. Returns the registers. Semaphores. It's kind of maybe crappy putting so many diverse things together. These have to go in their own cache line. I don't really do this very carefully, but I think when you use a lock, you're supposed to have everything in a separate cache line. I don't know what happens. I have lock bits that I'm not separating. I have structures with the lock, and I don't really pay much attention. As long as there's no other lock, I think it's okay. Anyway, it's pretty stable. It doesn't crash very often. Anyway, so hash table types. So I defined these are okay, where is the hash table? So this is the base. I have some C++ features. You can inherit or whatever you can have a base class, a single base class. So a source symbol has a hash as a base. These have my hash table is an array of linked lists. And anyway, it also has in addition to my hash entries linked to the table, they link to each other so that it's a sparse table. So if you want to quickly go through the list, you can use the next and last circular doubly linked list queue. Anyway, so various hash entries. There's my birds. So the compiler, the compiler uses the hash table, and that's for member variables of classes themselves. It's pretty strange to talk about classes when you're looking at the structure in the compiler for a class, but that's what we're doing. Some of these things. There's a function actually looks like a class, which is that's pretty strange, but oh well. So now we get into the document. I call these doll docs, at least that's what I call them in theory. They have dollar signs. They're not just text, they have sprites. So I have flags for the individual entries, and then we get into flags for the document main structure somewhere. There's the most confusing thing about this is these invert, select, blink, invert, select. So these are bits. I think they're maybe 28, 29, 30, 31. The individual entries have these flags, and then these individual, a lot of different places you see these four grouped together. They have to be in the same location, and anyway, it's kind of not straightforward. You see these are defined in terms of the entry flags. This is the document flag, and then these are the document entry flags. So a document is made up of lines of text, and there's a carriage return on each line, and that's an entry. We can look at the entry types. The entry types, you can have text, new line, soft carriage return. It'll store the cursor location in the file. A tab is a separate entry. Anyway, I better not get into these. I'm going to run out of time. So what else do we have? Let's go a little faster. So we have the document structures. That's the editor. You make when you want to do forms, this is an extension to the C language. You can put metadata in your class definitions, and then the form pop-up routine or the form routine will use these strings as the prompt for if you want to ask input data, you do a form string, a format string, and this is going into a widget, a doll doc widget. Anyway, I don't use a resource file. Normally you would do dialog boxes in a resource file. I don't do that. I like it all in one file. Well, anyway, so we're getting into the document. You have a lock that keeps different people from modifying the document. The screen updates, the window manager updates the different window. Each window has documents, and you want the window manager not to interfere with the editor when you're editing a document. So there's the window manager globals. These are compiler options. Now we're getting into the compiler internal stuff, the raw data types, and the intermediate code for the compiler. It's a stack machine intermediate code. Intermediate code, it's kind of complicated. What is this? CM code miscellaneous. Okay, that's getting into the jump. When you have a switch statement, you have jumps, and when you have string constants, those go into the that's all the junk that gets compiled and data placed after the function code. That includes string constants, jump tables. That's data that's part of the code, but it's in other compilers they have different segments for data, code, and stuff. I just put my data just after the code. And I compile function by function, just one function at a time, and then I put the data after it in the binary file, or if it goes into memory. These are this is for my assembler opcodes. Now these are some. Now we're getting into the definitions for registers. Now these right here tell. These are flags that tell what registers are used by the compiler, what's clobbered, what's preserved. Some of the registers are some of the registers are irregular. 12 and 13 are irregular. Anyway, that's because the SIB and modder. Anyway, so this is for the assembler, a bunch of stuff. This is the assembler addressing modes, flags, hash table. There's the opcodes go into a hash table. This is the binary file. The compiler makes a binary file. What's this? If it's making it ahead of time code, it uses that structure. Just-in-time code is actually easier to do than ahead of time code, than a binary file. If you think about it, isn't that interesting that just-in-time code is easier than ahead of time? So the lex structure is basically the structure it carries around as it compiles. The code goes into so everywhere in the compiler it passes a lex structure, and the lex structure has stuff like well, it has everything goes in the lex structure except the ahead of time structure. Okay, I put all my compiler global variables together, assembler, unassembled globals. PCI devices, that's not really used. ATA rep, well, ATA is the hard disk. The TAPI is CD-ROM. These are the command codes for the hard disk access when it's doing port I/O. File masks, boot record. Now we're getting into the Red C and the FAT32 structures, and the ISO 9660 structures. That's the file system for CD-ROMs. Now we're looking at the attributes, and when you make a directory, the Red C native structure. Now we're getting into file utilities. This is these are something you will use for instead of find first, find next like standard C. You use find files. Anyway, block devices. Now we're going to get into drives. Used to be called partitions. Drives. And this is the global variables for the disk code. The file access. What is this? Find. I don't remember what this is. Oh, C file. Okay, well, that's like when you call fopen. Fopen. I don't know why it's FF. Anyway, what do we have? The internal memory. This is for memory management. Heaps and block pools. Raster operations for the graphics. Here's the colors. The colors are defined. I went ahead and, if God said 16 colors, I made it for all time. So instead of doing this for a better namespace collision, I went ahead and I did it for, we know it's always going to be small scale because I set it a limit of 100,000 lines of code. So when you have bigger files, you want longer names. But mine is small, so I can use short names like that. Anyway, so keyboard global variables, mouse global variables for the mouse pointer and stuff. Input pointer is what I call. You might have a joystick, but we don't have joysticks anymore. You can make Control G, Control Shift G, Control Alt G. Make a grid on the screen. The scroll bars controls like a slider. There's a slider control. The menu at the top of the screen, that's what we're looking at. See menu. Exceptions, that's an internal thing for exceptions. What's SVC? That's server. When you have inter-task communication and if you put text in another task standard in, or you have a server task that has a master, then you do inter-task communication jobs and stuff. Messages get passed between tasks. My messages are stored as bits, and there's only so many types that you use. Windows gets thousands of message codes. I only have about 15 different message codes. So this is for tasks. Each task has a structure. FS points to the current task record. GS points to the current CPU record. TSSs that's the Intel low-level structure for a task. Mine is ring 0 only, and I never use the hardware task support because I never change privilege levels or anything. So if you're using the debugger, there's a alias for FS is the task record. So this will access this will access the stored register. When it does a task context switch, it stores the registers in the current task record. This is the CPU. GS points to the current CPU. I made an area for the page tables. I identity map everything. So I have a fixed size for my page tables. They're identity mapped. I go ahead and map. Right here is the limit of how many pages I map. It's set to 128 gig of RAM maximum. If you want more, you can change that. Scan codes and scan code flags. The scan codes are similar to ASCII, except it's for a keyboard, and on a keyboard you have things which aren't ASCII. The cursor keys are not ASCII, but they have scan codes. I put it used to be 2-byte scan codes. That's the most natural, but what I do is I put the prefix. There's an escape byte for bit 8 is a E0 prefix. If you know what scan codes are, you know what I'm talking about. What I do, instead of having an E0 2-byte code, I put E0 bit as bit 8. Normally bit 8 is for a new key. I shift it around a little bit. This is the device context for graphics. CDC device context. So it has a pen width, it has a brush. Basically, you can imagine that if you have two people writing to the screen, you want one to set the color to blue and another to set the color to red. Two different windows. Anyway, they need their own color for their device context. So, anyway, this is the compression routine archive. What do we have here? String utilities, string find, list, keyboard globals, sound. It'll record. It's only a frequency in it. If you're making a video, it will record what you set the frequency to. Debugger. What else we have? That's the end. Oh, good.